Sí. Bueno, ya veo live. Yo creo que ya estamos, ¿no?
Listos.
Ya estamos listos entonces. Bueno,
Ya.
ok, perfecto. Permítanme, tenemos hoy un invitado internacional, el profesor Jens Sørensen. I hope I speaking correctly your last name, professor.
Yeah, that's
Eh,
fine.
and, bueno, sean todos bienvenidos al Seminario de Fronteras de la Energía. El día de hoy tenemos al doctor Jens Sørensen, como ya les había mencionado. Bueno, en esta ocasión nos estaré moviéndome al inglés por nuestro invitado. Let me introduce the professor Jens Sørensen. He has a very nice topic and a very nice topic, which is challenges and development in wind turbine aerodynamics. So let me tell you about a little bit more about the Professor Sørensen. He's professor of fluid mechanics and head of section of aero and fluid mechanics at the Wind Energy Department at the Technical University of Denmark. His research interests include aerodynamics and aeroacoustics of wind turbines, computation of fluid dynamics, vortex flows, and biofluid mechanics. He has authored and co-authored more than 230 peer-reviewed articles with about 8,500 citations and H index of 44. He has been organizer of several conferences and symposia, including various UTAM symposia, FENS European Fluid Mechanics Conference, and the Wind Energy Science Conference in 2017. He's founder of the International Master Program in Wind Energy at the TU and co-founder of the Erasmus Mundus European Wind Energy Masters Program. Started in 2012. He has served as co-editor of Computers and Fluids and is today co-editor of Applied Science and Wind Energy Science. So he has a very long CV. He's just highlights of his career, and I think it's going to be an amazing seminar. So please, Professor, you can start sharing.
Okay. Yeah. Thank you, Carlos, for your introduction. So I'll share my screen now.
Yes, I will confirm that everything works fine.
Yes. And I think we are in presentation mode already.
Yes, it's perfect. Yeah. Thank you very much.
Yes. Good. Yeah. So, I was invited to give this lecture here. So I have collected some of my own work and some of my colleagues' works. And it's a big pleasure to be invited to this lecture series. So I decided to call it the Challenges and Developments in Wind Turbine Aerodynamics. And what you can see on the front page here is one of our two campuses that we have at DTU Wind Energy. So we are part of Technical University of Denmark, and this department here about wind energy was created about 15 years back as a merger between a national laboratory at Risø, who did a lot of work on wind turbines, and then some departments at DTU, including my own in fluid mechanics. So I'm now head of section in this department. And what you see here is some wind turbines. We don't test wind turbines so much more at Risø campus, simply because the wind turbines are growing very big now, and we do not have the good wind resources here to really test the big rotors. I'll show you later where we test them. But here's a collection of some of the wind turbines we have on a permanent basis on the campus, which we use for research, but we also use them to gain some money because they are operating and they produce electricity. So I also like, when I talk about wind power, to kind of state what is interesting and what are important in wind power. And the way to do that is really to distinguish between different topics. So the main topics here are, I would say, nature, technology, it's power systems, and it's society. So if we look at nature, we have the wind resource, which is very important because there's no need to put out wind turbines if the wind is not blowing. And also you need to know where to put the wind turbines in order to get the best power performance of the wind turbines. However, when you put up wind turbines, most actually of the forces acting on a wind turbine is not used for producing electricity. It's something you don't use for anything, but it gives loadings. We call it the thrust. And it can be very important. So therefore, when you design turbines, you design them both for, say, optimal power performance, but just as much as they have to sustain in very wild environment for like 25 years. So therefore, this is really important also, this part. And that also today includes wave loadings. So it's not only the wind, but we go offshore and then you have waves. Nature also has something to do with environmental aspects and also climatic aspects. When you put up, say, large and many big wind farms, then suddenly they can change the local weather conditions. So that's something we're also looking at the moment. Then we have technology, and that's mainly where I am. Of course, aerodynamics are important because that's the bone of the backbone of the wind turbine is really the propeller, the rotor, and therefore the design of this is very important. And that also includes elasticity. So the forces are acting on the blades, but all the forces are transformed into stresses into the whole wind turbine, including the tower and the foundation. And you need to be capable of computing all this. And therefore, you need an elastic model just as well as an aerodynamic model. And such a model we also have developed in my department. Besides that, there are machinery elements, you have generators, and you need to be capable of come up how to do the foundation of the tower. Today, a turbine is never working alone. It's always working with other turbines and or with other power systems. So grid integration is very important also. For example, you can see to the bottom right here, you can see here's a combination with solar panels, but it can also be a combination with many other energy sources. We also here talk about power to X, such that it's not just that you get electricity, but if you want to get fuel, for example, you need to, for example, do electrolysis in order to get hydrogen. We call it power to X. At the same time, when you talk about the systems, then the interaction and the layout of wind farms in itself are very important, and how also you have interaction between wind farm to wind farm. So they are, so to speak, stealing the energy from each other, and that's really important to include also in your modeling. And then the final thing we have is society. And society is, you could say, is not essentially all the non-technological issues. That's economics, that is societal aspects, that is not in my backyard discussion. It's also storage issues. It's things related to, for example, if you have animals or all things that are disturbed by, you can talk about all kinds of things that disturbs whether you feel that the wind turbines are disturbing people or the surroundings. That's related to society. And all these things you need to have a focus on when you want to introduce wind power into a specific area. Clearly, where I am is in this here. So it's mainly wind and wave loadings, aerodynamics, elasticity, and wake interaction. This is where I work, and this is where my section also works. But if you look at our whole department at DTU Wind and Energy Systems, then we are divided into 4 divisions. So we have one called Wind Turbine Design, we have Materials and Components, we have Wind Energy Systems, and then we have Power and Energy Systems. And there's many topics within these, and you can just read for yourself. What are, when we talk about materials, is of course the materials that the blades consist of, but it's also the, for example, steel, where you have the tower, and composites are very important there, both for analysis and for manufacturing and testing. We also have in power energy systems, it's another division. It's about how the energy system is distributed, how the energy market works. We have a specific power labs where we investigate, for example, the use of electric cars in society, and also people working on power to X and storage. And recently we also formed a group, and that is within, we call it Wind Energy Systems Division, which typically has to do with meteorology and remote sensing. But there we also now have a society and market and policy section. But we come up to the other one to the left, then it's wind turbine design. And that's, of course, the classical engineering disciplines with respect to the design and operation of wind turbines. And there we are 5 sections. We have, for example, testing and calibration. We have something related to elasticity, measurement systems, airfoil and rotor design, and air and fluid dynamics. And this is essentially this I'm going to talk about today. These are these 2 parts here where I'm head of section for the first one. So let's go a little bit to what we are doing in my section. And what I normally say, we are doing advanced wind turbine aerodynamics, both modeling and experimental validation. And if we, maybe I can make a small pointer here, then we can, well, yeah. So if we take that one up here, so this is a part of a landscape, and you can see some ISO contours behind in a cross section. So part of what we're doing, we are analyzing flow fields around different landscapes. We call it complex terrain typically when we talk about wind turbines. And we have CFD modeling of complex terrain as one of our tasks, where we simply can take a specific region in the world and get an isosurface plot of the terrain, and then we can do a computation, fluid mechanical computation of the flow fields. So this is a kind of, you could call it micrometeorology. Many times we combine it with real meteorology because we collaborate with the meteorologists we have of the department. A big part is related to wind farms offshore, and that is of course in opposition to where you have these more complicated landscapes. But here the wind turbines are located relatively close to each other, so that we have these wake effects where there's a shadow between from one wake to the next, and this is very important to be capable of simulating these. I'll come with some examples of this later. And then we go down in scale to the rotor. So here we can see the rotor. We have one here, and you have the tip vortices being shed here, and you can see how that deforms. We also do detailed analysis where we go into the structural part of the wind turbine blade. So either we design a wind turbine blade or we design parts of a wind turbine blade, typically in collaboration with manufacturers. For example, here it's a detailed design of the root section of the turbine, which has paid a lot of attention. We also go into airfoil design, and also look at the characteristics of the loadings on airfoils in order to optimize them with respect both to performance and low noise reduction emission. And we have a case here also, but it could look like an aircraft. It's not. It's actually the inner part of a wind turbine blade in which we have made a hole in it in order to put up a slat in a part of the blade. So there are some examples of some of our research activities, and it has a lot to do with different scales, you could say. So we go from the small scales, it's the airfoil, and the biggest scale is the wind farm and a complete landscape. And all this needs experimental validation. And we have access to data, for example, from turbines in the nature. It could be at the Risø campus, but also from manufacturers. We also have a rotating test stand where you can do specific things on a blade. And then we have wind tunnels also. So that's the main thing. For example, testing. One thing we have made is a blade test center. Clearly, all big companies, they have their own test center. For example, here is from LM Wind Power in Lundeskov. And it is like they have very long blades. So the longest blades today, they are up to about 120 meters. So you need really big facilities to do a testing. And we have a big facility, but not that big. So what we do is we do model experiments or tests on blades using a specific method in which we actually can mimic what would happen on a real larger blade using some model analysis. And this is this, unfortunately, not a person standing here, so you can't see how big it is. But this big block here, I think it's about 3 meters high. So it is still a big facility, but not as big as the one the manufacturers they do for blade testing. Then we have wind tunnel for airfoil testing, and we are operating that wind tunnel and own it, and it's at the Risø campus. It was built for a few years back. It's called the Paul la Cour tunnel. Paul la Cour was a Danish physicist who was a wind turbine pioneer, and so in honor of him, we call it the Paul la Cour tunnel. But this tunnel here is for design of airfoils, so it's mainly used by industry. We also use it for experimental purposes, but it's extremely expensive to run. So we can only afford to run it ourselves in some very dedicated projects. But the industry likes to use it because here you can test both for airfoil performance, but also for noise emission. So it's an anechoic wind tunnel. And that's really a nice facility to have, and that also makes that we have a very good collaboration with industry, which we always think is very important when you're doing wind turbine research. And we are about the total number of people employed at the department is about 450 now. So it's quite a big department compared to that. We are only doing research with respect to wind power. But it is a big industry in Denmark today. We also have test stations, and actually the Risø campus started as a national laboratory in '79. You can see on the other one here where they tested kind of pioneering wind turbines at that time. So there were many different concepts, as you can see here. You have the diode turbine. You have a Risager turbine, which was an old-fashioned turbine. You have a gyro turbine here, and many different others. But today we barely see these anymore. You always see turbines as three-bladed, upwind running horizontal axis machines, and then they can either have a gearbox or a permanent magnet generator. In 2007, we made this test plant here in the more windy part of Denmark in order to test the big wind turbines, and that we do for industry. And in 2011, we even went out further and more close to an area where you are very close to the ocean, Østerild. And this is a picture here from Østerild today, which is a national test center for large wind turbines. And here we have 9 places now for these wind turbines, and 4 of them are occupied by companies already. The rest we rent out to who wants to rent them, and they're fully booked all the time. And what we do here, we have a small group. I think there are 5 persons doing helping the companies doing the experiments, so with experimental equipment, but the data are of course confidential. So this is where the big companies they run their tests. Okay, a little bit back to what we are doing in my section. A lot of what we're doing is based on CFD, computational fluid dynamics, and probably not of any secret for any of the audience here, but the basic elements in CFD is that you solve the Navier-Stokes equations. You need to make mesh generation. You need to model turbulence. You need to have access to efficient computing algorithms, or you need to have developed some efficient computing algorithms. You need access to high-performance computers, and then you need good post-processing facilities. And today that has become really a standard. But we have developed our own CFD tools through the years, starting about 30 years back, and we have some, tailor-made CFD codes that we use as a part of our research. But I think many people now, they use OpenFOAM or use other kind of CFD tools that are available online. Just to give an example here of, or some examples of where we use this, it's ellipsis code. It has both a 2D version and 3D version. And we use it, for example, for airfoil simulations. It could be two-dimensional airfoil simulations. Then we use Reynolds average Navier-Stokes simulations, or it can be unsteady Reynolds average Navier-Stokes simulations. But these you can keep in 2D, and that is typically when we do design of airfoils. We use this technique. Then, if you want to learn more about the aerodynamics on the airfoil, you go to a 3D. For example, large eddy simulation or a detached eddy simulation. There are different types of closures you can use with respect to turbulence. And also we have started recently doing some DNS, direct numerical simulation. They do not demand any closure of your equations with respect to turbulence, but they're very computing expensive. But we can gain some information that can be used in your models. Then we also have rotor and park simulations, and there are different kinds. We have few of them are fully resolved geometry. There you can only afford typically to compute the flow for a single turbine in the near wake. Otherwise, you have to go to actuator line or actuator disk modeling. Then you can have more turbines in your simulations. I'll come back to this later here. And then you also need some fluid structure coupling. And we have essentially two elastic codes that we're using. The one is called Hawk2 and the other one is called Flex. And the reason why we have two is simply because the DTU, we developed the Flex code, and at the Rijksmuseum National Laboratory, they developed the Hawk code or the Hawk code. And then we merged, and now we have two codes. So, but we are essentially mostly using the Hawk code. And that's typically for fully resolved or actuator line, actuator disk formulations. We do both. And of course, when we talk about airfoil simulations and optimization, we also do rotor optimization using OpenMDAO framework. And then we have these atmospheric boundary layer simulations where we can do both the flow, but also, for example, stratified flows. And we say that ellipsis is really important for us. It's a central workhorse in research projects, and there's also licenses. The industry use it, the code also on a license basis, and it's also a computing core in all of the tools that the department either use or sell to the companies. So what kind of research do we do? Well, one could say that, okay, wind turbine aerodynamics, that should have been mature now, but actually it's not. Some of the reasons is that the rotors are becoming larger and larger, and they're becoming more and more slender. So therefore, you have much more dynamics of large deformed rotors. For a motor and wind turbine rotor of, say, more than 100 meters, typically it's pre-bent, and the deformation of the tip while it's operating can easily be 3 to 4 meters, which you need to have included in your simulations. So this is some complications. Also, you could say it's a complex geometry. When you're talking about grids, you need a grid both which covers the rotor blade, but which also is steady. So you need to have some interaction between these two, because the tower is steady, whereas the rotor is rotating. So you need some overlap between the gridding. We also been looking at the new concepts like introducing adjustable trailing edge flaps as you have on aircraft. There we have also tried to simulate that, but we also have tried to put a real trailing edge flap on a megawatt turbine and see the effect of that. Then also we use always wind turbine blades today what we call aerodynamic accessories. For example, vortex generators. There could be blowing or gurney flaps or roughness tape, but at least vortex generators and roughness tape is really inherent in nearly all design of wind turbine blades today. So we need to be capable of modeling that as well. Then you have 3D stall including laminar turbine transition. That's a very classical fluid dynamic phenomena, but it's still important, and we have not been capable of solving it completely. So there's still lots to do there. Then we have all the inflow we are talking about. That's really turbulent. It's from the atmospheric boundary layer. So it's both unsteady, three-dimensional. It has gusts. It might even have low-level jets, and there can be many different ways, and that you need to model correctly. And of course, you have the interaction in complex terrain between the roads and the terrain. And wind power methodology is, in a way, getting closer to wind turbine aerodynamics. So these are start to benefit from each other. And now we also go offshore. So it's combined wind and wave loadings. And one thing more is actually we are now going into floating wind turbines, which gives an extra degree of freedom that we need to take into account also. So there's still a lot to do for people working on wind turbine aerodynamics. But first, let me go back to a very old, relatively old simulation. That is the first CFD simulation, probably the first ever. And that was my colleague, Niels Sørensen, who made that. And that was in association with the American blind test competition that was in 2002. So it's about a little bit more than 20 years back. And what he showed here in these competitions, if you follow here, you see the red spots here on this blade, which was tested in the NASA Ames wind tunnel, there were pressure taps here. So it was a blind test. So nobody knew about the results. And when we saw the results from a lot of research groups worldwide, there was a big scatter. But there was one simulation that actually turned out to be very consistent, coinciding with the experimental data, and that was this CFD simulation. And as you can see on all cross sections, where the straight or the solid curves are the computations, and the circles are measurements. And it's a pressure coefficient. So this is not so important, just to show you that everywhere there was a very good comparison, both near the tip and near the root, except at one place, and that was this one here. If you look, the measurements did not show any trace of a pressure peak or suction peak, as you have it here. And that was a kind of a mystery. Why is there no such suction peak? Because you should have it. It's an airfoil. And then it turned out, and that was what you saw in the CFD simulations, actually there was formed a vortex here. And that vortex was located in the simulations a little bit off compared to the measurements. But if you put the red line here, you would have exactly that signal here without any suction peak. And the reason is that it turned out later on there's a small kink in the surface of the blade that was designed, and that you couldn't see from the experiments actually. So all what you see here with these limiting streamlines is what you got from the CFD simulation. So that was actually the first eye opener that doing CFD on wind turbine blades is very important, and that you can actually gain some new knowledge as compared to what you otherwise would have. And since then, we have used CFD for many different purposes. For example, we have looked at airfoils with trailing edge flaps, as you can see a simulation here, to see what are the effects of that if we can control some of the flow behavior around the airfoil. So that's one case. Another thing here, we use the CFD technique for design of airfoils. And you can see here how it's, the dynamics of doing different simulations. And it is such that wind turbine airfoils have very specific properties. They are very different actually from aircraft airfoils, because they need to be insensitive to roughness. And that typically means that, as you can see here, that the leading edge gives a very specific shape, which looks a little bit like a whale, the shape of a whale. And that is because you want transition to take place at before you reach the suction peak. So in order to have this phenomenon where you get insensitivities of roughness, and the reason why you want that is that roughness will appear always because of, for example, insect in the air, dust, rain. So therefore, you'll always have a surface that is not exactly equal to a smooth surface as you have on an aircraft. And you never clean a wind turbine blade. You don't do that because that will be very expensive, and many times you can't do it. Another thing we also use the CFD thing for is to extract airfoil data. And we say this is the 3D airfoil data. So they are different from the 2D ones because they have, because of Coriolis and centrifugal effects, they are modified. And they're actually mostly modified near the root, where you also have, typically you have a separated flow. But doing some analysis of the resulting computations, you can actually come up with the corrections for the measured airfoil data, the airfoil data that's measured in the wind tunnel. And we have done it in many times. We have done it in different ways, and it seems now that there is it is actually possible now to come up with very good corrections for these 3D effects and put it into some simplified formulas. But everything is based on the CFD simulations here. Also, the vortex generators I mentioned before, we do some research on. So we have developed a new type of vortex generators, as you see here. They are kind of shaped as a delta wing, and they are a little bit better than the usual ones. So we hope we have a contact to a company and hope that they would be interested in developing further and maybe use them in a production. But in this case here, we have actually put them into our CFD solver and solve for the full flow field. So there are essentially two ways you can either do a CFD simulation along a surface with the vortex generators. The way they work is that they create behind them two strong vortices, which helps mixing the boundary layer with the ambient flow, and that strengthens the boundary layer and makes it stronger towards adverse pressure gradients. So that's one thing. But the other thing is also, if you want to do it for a full blade, you cannot model them in detail. So therefore, you need to put body forces into your computational tools. So that we have also done. And so you can both design a blade with vortex generators, and you can design the individual vortex generators in order to give them optimum performance. Also, integrated aerostructure design is something we're working on now. And actually, we have a lot of computing codes that we need to combine, because they need also to go into the details of how what materials you use for the blade and how the inner structure of the blade looks like. And that means suddenly that you optimize the blade not only for performance, but also for lifetime, for example, in the same process. And this is an example of this here, where I'm not going to detail, but we have a lot of different codes that you can put in. You can increase the complexity of types of materials and also the design of the inner part. And you can gain a little bit on that. And we hope that in the long run that some of the wind turbine manufacturers, they'll start to consider this also, because they can save actually a lot of money, because they can save material when they design the blade. And this is a little bit of the same here. We have different techniques, but one thing that's very important is to have an adjoint solver. And that has, in order to make huge computations, looking for steady solutions and looking for design solutions. And we are working on this adjoint solver, and we are pretty close now to have a full developed adjoint solver for this ellipsis code. But this is work that has been going on for, I think, 5 years now, but we are getting closer now. And we also, here, just to finish about the rotor stuff, we are doing it also. For example, we have been looking at winglets, as I mentioned before, rotors with slats. We have been looking at hub design, specific hub design, and also putting in the vortex generators. So just some examples of CFD use. But then I'll talk a little bit more now about actuator disc and line technique. So all up to now I talked about is when you have a fully resolved rotor. the point is, if you want to go into a wind farm, you need to do something with the rotor, because you simply do not have computational power both to resolve the boundary layer on a rotor blade at the same time as you want to solve the flow in a wind farm. So you need to focus on part of it. And that's why we developed this so-called actuator disc or line technique. And the basic idea is simply that we replace the rotor blades by body forces, and then we determine body forces from airfoil data, and then the flow is simulated typically by large city simulation. So what you can see on this here, this is a domain, and it can even be long. Now this is only one turbine, but it could be a complete wind farm. Then you typically use an actuator disc, and then you sacrifice some of the mesh points on the blades or on the rotor disc, and instead use them for the large scale structures in the wake. So the basic of the actuator disc and line modeling is that you use the filtered or average Navier-Stokes equations. The load model is based on airfoil data or prescribed from some prior knowledge of the turbine. In the actuator disc model, the forces are distributed on annular elements on the rotor disc. In the actuator line model, the forces are distributed along lines representing the blades. Then you need a turbulent inflow model to represent the atmospheric boundary layer. And very importantly, you need actually a regularization function to control the force distribution. And then there can be different correction tools for tip effects or finite aspect ratio errors. So that's the basis. And I'll not go too much in detail, but the idea here is that the red line here is the actuator line, and essentially the blade, and then you have a grid. It could be Cartesian, and then you simply interpolate between the two. So one of them, you from the grid, you find the local velocity field that you transform to the line. On the line, you compute the forces, which you then, through the regularization function, put on the grid lines. And then you can do a simulation without knowing all details of the rotor blade. And what comes in is a body force into your Navier-Stokes equations, as you can see here. And here's just an example where if you want to use a blade element theory to find the forces, you can do it in the very same manner as you do for a blade element momentum theory. So that's, but we also been working now on putting in generic forces, and I had a few papers recently on that, a new model where you can come up with analytical forces, so you don't have to know actually what kind of airfoils you're using. And what do we use it for? Well, we use it typically for studying wakes around clusters of wind turbines or for full wind farms, as you can see here. So depending on what you want to look at, you can do either the actuator disc or the actuator line modeling. And it is simply to make simulations capable, or computers capable of doing these simulations. So if you look at scales in wind energy, we have some characteristics, length scales going from, say, boundary layer of an airfoil is in the order of a millimeter. And if you take a rotor, the length of a rotor is in the order of 100 meters. The size of a wind farm is in the order of, say, 10 kilometers. So there's a really huge range, a spectrum of length scales. So here is the 7 length scales, and you cannot cope with that in all space directions. Fortunately, there are only 2 velocity scales. You could say it's the tip speed or it's the wind speed. So you say that's either 100 or 10 meters per second. Then you have time scales, and these you find simply by dividing lengths with velocity. And you can see they go from 10 to minus 5 seconds to 1,000 seconds. So all this you can of course not cope with in one simulation. So therefore, with this technique here, we are restricting ourselves to something that goes from, say, the airfoil cord up to the wind farm size. And that suddenly makes it possible to do the simulations. And therefore, we can now start to do wake aerodynamics. And we know a lot now about the wakes, among other things, because we have this technique. But if you go back some years back, we essentially only knew what was happening in the near wake and in the far wake. In the near wake, you have kind of the footprint from the loading on the rotor that you know from the Bate element momentum theory. And in the far wake, you know you have self-preservation and similarity to typically get a Gaussian velocity deficit. But what happened in between, you need to model. And there are, of course, a lot of analytical models, but they are made on assumptions and then some calibrations to measurements. But now we actually can do it with the actuator line model. We can start to study what's happening in the wake. And these are some of the very first actuator line models computations that we did. And here we have 3 wind turbines along the same line. And you can see at the upper one, you have laminar inflow. It comes in here. It generates some tip vortices, but actually instability starts first to appear when these vortices hits the second turbine, and then it goes into small scale turbulence. Whereas if you have a turbulent inflow, as you can see on this one here, then you can see that already, say 1 or 2 diameters behind the turbine, the tip vortices start to break down and start to generate small scale turbulence. And even with meandering, you can see how the wake here meanders when it reaches, it goes down into the far wake. But there are some very basic research questions still when we talk about wakes and wind farm aerodynamics. And some of them we have answered, some we are still working on. But for example, what is the relationship between the strength of the vortices and the blade load? That we know very well today, actually. How important is the dynamics of the vortex system? That we know more about now also. What are the conditions for instability? What do we mean by near wake and far wake? Can we come up with a more clear definition of that? What is the relation between the dynamics of the vortices and this large-scale meandering or the movement of the whole wake? Then the question about added turbulence intensity. How do we model that? So we have the turbulence in the inflow, but we also have the turbulence generated by the wind farm itself. How do we cope with these such that they can be added, and how is that related to the loading? Then, of course, performance predictions and optimum layout of wind farms is very important. We also need to find the lifetime estimation of lifetime of the turbines in a wind farm. And then, of course, atmospheric stability is important now. And also wind farm to wind farm interaction is very important. So there are many questions. And we have every second year together with Stephanie Vanel, I'm running a conference in Sweden on the wake and wind farm aerodynamics. And there are about 100 persons coming there now. So it's a very nice conference, actually, at the island of Gotland in the Baltic Sea. I'll go a little bit more into vortex instability. So I have some of these visualizations. Here's one from this blind test competition from NASA Ames. And here you see that it seems that the tip vortices are completely stable. At least we cannot see any trace of instability. Whereas here's one from our campus, where you can see suddenly some kinks appearing here, even though it's a relatively stable day. And there is a question, of course, what are the conditions for these tip vortices with respect to stability? I did some work with Valery Okolov. It's years back now, but we did an analysis, a stability analysis, which was analytical and actually on tip vortices using the so-called model, far wake model of Shukovsky, where we simply assume that the tip vortices form helical structures. And from that, we found actually that the vortex wake behind the wind turbine is unconditional, unstable. So it will break down. And that we have seen later on also, for example, from many different experiments, but some of the very first was from Feli, which you see here, which was shows a breakdown of the tip vortex after a ship propeller. And today there's been a lot of research on this, so it's really now pinpointed what is the background for this instability. That is this mutual induction instability we see, and that is typically because there's an interaction between the vortices themselves. So it's a little bit complicated because they're helical, but it is essentially this phenomenon. And yeah, this is not so important here. So, but if we do a simulation using an actuator line model, then we can come up with kind of a characterization of a wake, as you see here, which is from a simulation. And we can see here that if you go from 1 to 6, it starts by the vortex system being formed by the circulation on the rotor blades, first thing. Then you have rolled up into a center vortex and distinct tip vortices, 2. And then you have destabilizing of the tip vortices, and that takes place through a linear amplification. And then there's a breakdown into large-scale turbulence, which you can see in 4 here, and then you have turbulent mixing. And eventually, when you come to the far wake, then you have meandering also. So that this gives kind of a sketch of what's happening behind a wind turbine in the wake. We like to distinguish between 3 areas. The first part where you have linear amplification, and the next where you have, we call it nonlinear transition, that is where all the scales, they start to merge. And then you have the last part where you start to have a Gaussian velocity deficit. And when that appears, then we are what we call in the far wake. And we have done some stability analysis numerically to detect how this appears. And I'll just show you briefly some results from that. What you see here is the flow on the rotor. Of course, it's rotating, but we are in a rotating frame of reference. So what we do here is we put in some perturbations in the loading, and then you can see how that propagates downstream and eventually gives an instability. We see the same here from the side. So you can see that it starts a little bit in the middle here. There's always something at the very end here, but that's due to outflow condition. So what you should look at here is about here. Then you can see there. Now you can see it starts to move. So that is vortex pairing. So these vortices, they start to pair with each other. And there is actually a very nice theory developed by von Karman originally about this vortex pairing that we can use. And we have also looked into different modes, and it turned out there are some specific modes that are much stronger than other modes. I'll not go into the detail of that, but just show you how we could model the length of the wake simply by saying that we divide the wake into 2 groups. The first was the way you have linear amplification, and the other one where you have this nonlinear interaction. And for the first part, so here we have the wind turbine is actually located here. So this is just an axis. And this axis is measured in rotor lengths. And we put in a perturbation, and then we look at the amplification of that perturbation. The perturbation can have different amplitudes, small one, a large one, a medium one, and a small one. And but then we simply follow the from the breakdown position, we follow on the screw surface of the tip vortices the amplification, and we find the amplification rate, which is called sigma. So it looks like that. That's very classical amplification theory. So it has an exponential amplification. And at a certain point downstream, it will stop being linear and it will be nonlinear. And that is that we could call it a very, very near wake when that happens. And then after that, there'll be a nonlinear transition, as you see here. And depending on how big your initial perturbation was, then it will happen at different positions. So the smaller perturbation, the longer time it will take before it will break down. The slope of this here is actually the sigma. Then now it's referred here to lamp. Actually, it's von Karman who came up with this very interesting expression here by looking at 2 lines of point vortices. And then he found that the amplification of the amplitude when they start to merge, it gives this relationship here where h is the distance between the vortices and gamma is the circulation. And that is a starting point. When you have that one, then if we can kind of relate h to the rotational speed and gamma to the loading, and that's actually possible. And this is what we do here. If you take a typical helical shaped wake, as the one was defined by by Betts in his very pioneering work back to the 20s when he did his PhD. Then we can do the geometry of the wake in order to find this H, and we find it to be related to the number of blades, the tip speed ratio, and other properties, as you see here. You see here is the convective velocity of them. But this is pure geometry. If you assume a constant loading as approximation, you can actually find the circulation from this expression. So suddenly you have an expression for the dimensionless amplification rate, which looks like this. I know this is a little bit technical, but it's just to show you how it works. And all this can be related also to an equation. So I'm just show the final result here. And that is that you find an equation here for an expression for the near wake. So that is the length of the near wake. The first here is the linear amplification, and the other part here is where you have the interaction, the nonlinear interaction. And you can see it's the length of the near wake is inversely proportional to the number of blades, the thrust coefficient, and the tip speed ratio lambda. And then it's proportional to the logarithmic to the turbulence intensity. So, and we have validated it. It seems to work quite well, this expression here. So that can be used when you want to find out what are the, say, the near wake lengths before it's fully turbulent downstream of the turbine. Then we have also done some simulations using our techniques here for wind farms. And I can see the time is running out now here, but let me just finish with some of these. So we have a big wind farm close to Copenhagen. So this is Copenhagen area you have here on this map, and you have Malmö in Sweden. And then you have this Swedish wind farm located down here. It's called Lillgrund. And it looks like this. So each of the red spots is a wind turbine. And you can see there's kind of a hole in the middle of this wind farm. And that was because there was a ship that was used in order to put up the installation of the wind farm. And it needed to maneuver somewhere. And this made there was not space for a wind turbine here. So there's missing 1 or 2 turbines here. Anyway, that's very nice for us when you do research, because then we can see the impact of the distance between the turbines. So we have done simulations using actuator disk modeling of this wind farm. And then we're looking what happens for the power performance along a line where there's no hole, and another one where we have this kind of hole in between, or longer distance between the turbines. And the result came up was like this. So this here, if the first wind turbine in a line have a power production of 1, then the next one have only about 30% of that. And that counts for all the rest because of wake effects when the wind is along the line. On the other hand, if you take a line where you are missing a turbine because it was not put there, then suddenly you'll see that the turbine that is number 4 instead of now has a double production, because the wake has a time to recover due to mixing, etc. So it will produce double as much as the turbine you have over here. So actually, you could say you save the expenses of 1 wind turbine by having that hole. And of course, what that essentially tells us is that you need to optimize the layout of wind farms. So this work here is from 2015, and I showed because it was the very first wind farm simulation ever with actuator line model, which I did together with Carl Nilsson from Uppsala University in 2015. We have also been looking at simulations where we have an interaction between the land and the wind farm. And this is what you see here. So this is actually the eastern part of Denmark you have here. And then there's a wind farm out here, which is called the Anholt wind farm. And there you can see from simulation, that's a range simulation by one of my colleagues, Paul van der Laan. You can see that there are different effects, both from the land side and also from the layout side. So where you have red spot is where you have a high power production, and the blue spot where you have a low power production. And you can see due to the influence of this peninsula, this part here for winds going in this case in the western from the western direction, will have a smaller production than at this part here, where they are not in leeward from the land side. So that gives also an idea of that it's important to do these simulations. And then I think, well, this is not so much important here, but then this is my last one here. That is for wake modeling in complex terrain. What we do here is you have a terrain where we are solving Stokes equation around. So we have an idea of how the flow looks like from CFD computations. And then we do an analytical wake assessment. So we, after each wind turbine, we simply put in a wake that corresponds to that wind turbine. And then we see if it hits all wind turbines. And then we can do a simulation in which only part of the flow needs to be solved. So you don't need to take into account the wind turbine at first, but you first do it in the next step. And that makes it possible to do a kind of an optimization of where you are going to locate the wind turbines in the landscape. Okay, I think that concludes my presentation here. I hope you enjoyed it, and I'm happy to answer any questions you might have.
Yeah. Thank you very much, Professor. It was very, very interesting. I have a lot of doubts, but I can ask if there is any questions regarding the presentation. I think Eduardo has a comment. I don't know. His microphone is turned on. Professor? Okay.
Yes.
Okay.
Thank you, Carlos. If I can make a very, very general question. Thank you very much, Jens, for the presentation. Very interesting and very impressive work that you're doing at DTU. I was wondering, given that you have so much background and perhaps foresight for what's going to happen in wind energy in future, given that there is evidence that the atmosphere of the Earth is changing due to heating, global warming, what do you think would be the impact on energy production in wind energy production, both from the economic point of view and from the technical point of view that we should be aware of if we want to make interesting research proposals?
Yeah, I think what is probably the most challenging part in the future for wind power is the extreme events, because we see that they become more and more important, and we see them more and more often. So every year you have a new record in wind speeds and in rain, for example, and also in temperatures. And these give some extreme conditions also for the wind turbines. So they probably need to be designed for much higher loadings than we anticipate today. So that's at least one thing I can see. Then there has some has come up with ideas that maybe the wind turbine can protect cities if you put a lot of wind farms close to a city. I don't know actually, because I don't think we have seen any evidence, but there might be something in this also. But I don't think you should. It should not be the main purpose, though. The main purpose should be to harvest some energy. Then another question is, will the turbines cause any climate changes? There has been some studies, and you can see there are locally some changes in temperature because of the wind turbines. There's no evidence that it has any serious impact, so I don't think so. I think the main challenge is probably first these very strong weather conditions, and then also the impact of the wind turbines on the the animals living around them and so on, if you put them in large scale. I don't know if that explained exactly what you asked.
No, well, yes, thank you very much. That's very interesting, your reckoning, because In Mexico, as you might have guessed, we have hurricanes, and we have hurricanes that are more often coming to Pacific or Atlantic, and more intense hurricanes. So what you have just said is, I think, especially important for us. I don't know how it is in Europe, but for Mexico, that's a very, very appropriate.
Yes.
Thank you.
Yeah. Okay.
Thank you very much.
Thank you very much, Professor. There is a question in YouTube, which is focused on the wake development. He wants to know about the double peak profile near the wake, if there is any physical significance.
If there's any physical significance of
yeah, if there is a I think is what I understand is that if there is if there is any physical interpretation about the double peak near the wake, what is causing this double peak and so on.
I mean the wake is well, I'm not sure I'm understanding the question, but at least I can try to elaborate a little bit.
Yes.
The wake is important for the next turbine because it has a huge impact, not only on production of the next turbine, but also on the loadings and fatigue properties. And what we don't like is, we try to avoid is, for example, tip vortices enter into a next turbine, because that will give very strong, abrupt loadings. Another thing is that the vortex system in itself is interesting because it gives a footprint of the flow. So if you use, simply use the Savart law, if you know the vortices, you also know how the velocity profile looks like. So if you have designed an optimum rotor, then there are different theories. But for example, the theory of Betz was that the optimum rotor has to create a helical screw surface of vortex. And we know this is just an idea, but nevertheless, today you design propellers due to that, for example, aircraft propellers. And I think that in real life, maybe I should say that the idea of Zhukovsky originally was only tip and root vortices. In real life, you probably start by creating a vortex sheet, like the Betz case, but after maybe half a rotation, it will develop into strong tip vortices and root vortices. So it's always a mixture.
Thank you, Master Professor, for interpreting the questions. There is Sergio Cuevas, please, if you want to ask your question.
Yes, thank you, Carlos. Thank you, Jens, for your nice, interesting presentation. I have a very specific question about the size of the blades. You mentioned that they are growing. So I wonder if there is a practical limit for that growth. I mean, in terms of performance of the blade, how is what is expected? So if you grow the size, is there a practical limit or a limit in terms of performance or efficiency of the blade?
Yeah, I think, I mean, if you look at the structures as such, then the limit is not to see at the moment. I think the limit will come because they become so big now that they go out of the, at least for some days, the atmospheric boundary layer. And up there, if you come up where you have these strong, you have some what we call lower level jets. If a blade is subject to that, and we know that happens sometimes now, they can appear down to 300 meters, for example, or 200 meters, and you go up there now, then the blade will encounter a strong force when it's up and a small force when it's down. So that at least that is one thing. But I think the main reason why there are some today, there actually manufacturers don't like to make them bigger, because it only complicates life to make them bigger. They want to make them better, and they want to make it the fabrication of them much more automatic. So automation is much more important for companies. But the problem is that there's a competition, so that the one with the biggest turbine is typically the one that will be sell his blades. This is still like that. But I know they are trying to come up with an agreement that we should stop now making them bigger, but instead making them better. But there's as such no real physical limit yet with respect to that. But you have to understand, every time you make it bigger, you need to have a bigger crane. You need to have a much larger infrastructure. You need other these ships or vessels they use when they go offshore. Then you need to make new, bigger versions of these. And that is really a complication.
Okay. Thank you very much.
Thank you, Professor. Alan, did you?
Yes.
Thank you
Thank you very much, Professor, for talk. It was very interesting. My question is, if you can talk about what are the main points to take account if I want to do atmospheric boundary layer simulations for representing a wind farm? How can I incorporate a real flow to simulate a wind farm in complex terrain? I think it's very hard.
Actually, I'm involved in 2 European projects at the moment where we look at inflow data from atmospheric boundary layers. And we try to look at all the cases we know are of importance. So we will try to create a database that can be used by other researchers worldwide. But how do you put it in there? But one thing is that you, of course, you can do a precursor simulation. I don't know if you're using LES or RANS, so it depends a little bit on what kind of simulations you're performing. But we have that. There are some synthetic turbulence models you can use, which are the ones we use today mainly. So either you have a precursor where you do an LES simulation upfront until you get desired properties, or you can use a synthetic turbulence model, like we use a lot the model developed by Jacob Mann, the so-called Mann model, which gives a specific turbulence, but there's always homogeneous. Another thing we have tried to work on is to do prescribed body forces, also to mimic the velocity profile. But I don't know, I mean, my old colleague Niels Troldborg, who did his PhD thesis on the actuator line model, he did that a lot, and he's still working on that. But I don't think many researchers are using this technique because they feel that you are in a way cheating because you prescribe things that should come by the equations themselves. But it's complicated. For example, if you want to do a diurnal cycle, really to create something that is what you see in nature. So I think you need to say that simulations, they are different from what you see in nature, but they should mimic as much as possible what you see in nature.
Thank you. Thank you very much.
Professor, in that sense, for example, what do you think about the tendency methods, for example, which try to incorporate the information from mesoscale modeling, and then you as a body force, you introduce in the Navier-Stokes equations and try to it's not quite like nudging, but you try to incorporate the
I think I lost connection now. Can you try again?
Can you hear me now?
I don't know if that's my computer.
Can you hear me now?
Yeah, I think I have an I can see I have an unstable, but I can hear you now, I think.
Okay, can you hear me now?
Yes, I can hear you now.
Okay, awesome. Yes. What does try to say is that, for example, there is a tendency method that try to incorporate mesoscale information from global synoptic scales, right? And that information is incorporated as a source term in the Navier-Stokes equations. So what do you think about that kind of methods?
Maybe I should say something more general first. We have 2 groups, at least we have in my own group, we do CFD simulation, So we could say it's micrometeorology. So we're concerned about the wind turbine and its surroundings. But this other group, they come from atmospheric physics. So they do the big computations for, say, weather forecasting and the big fronts and so on. But they are including more and more wind farm in the simulations by different means. In my opinion, it's not good enough yet. And what we are doing, we are extending our domain more and more. And we are more or less meeting now each other from micrometeorology to mesoscale meteorology. And I think we can learn things from each other. So we have actually been discussing that we should make a specific version of WRF, which we include some of the things we use in our micrometeorology model. For example, the way we model the wind farm, because in WRF you'll model it typically as a roughness elements, but this is not detailed or good enough. But I have, for example, Paul van der Laan in my section. He's working very much on how you can do it in a more correct manner, which is still feasible and how we incorporate the forces, the real forces from the rotor as good as possible.
Okay, and for example, there is no Alan. There is any question in YouTube? If not, I can. Okay, for example, you mentioned two wind turbine models, which is mainly if we don't incorporate the geometry itself, right? For example, actuator this and actuator line. But for example, in actuator line, you need to know about the geometry and aerodynamic characteristics. Yeah. So if we don't have any of that, you mentioned your paper about some kind of forces which you can incorporate, which can make like a simile of the aerodynamics behavior for the wind turbine. So if we don't have that information, which what can I do? So what else can I?
What you can do is use an analytical load model, and
yes, that one, yes.
Yes. I have publication. It came recently. I think it was end of last year. I had something before, but now it was originally made for the loading for an optimum rotor, but it has been extended now. Also, when you start to pitch regulate and you go away from the optimum case. But this model you can use. It's quite easy to use. It's just some analytical expressions, and the only thing it demands is that you know the CT and CP value and the tip speed ratio.
Oh, okay.
Then it will give you that complete loading along the blades for any given combination. So, and it's done with I would say relatively good accuracy. It shows also that most wind turbines are probably alike because they're designed more or less with the same tools. So why should they be different?
Yes.
An optimal rotor should be an optimal rotor, but you can use that model, and if you're interested, you can just send an email. I can send you a script also that will give you. Then you can see how it works.
Okay, thank you very much, Professor. And another question is, or another comment is about you mentioned that there exists the presence of low-level jets. Yeah. But for example, how you incorporate the information of the low-level jets in your CFD models, because you need to know the temperature profile and also the shape of the boundary layer, right? So you with those information you incorporate in the CFD, or how you handle that?
Actually, you can do a CFD simulation where it will generate it itself. It has to be on a stable boundary condition. So where you will have an upper layer. So a CFD simulation without a wind turbine, as a starting point, you can generate a low-level jet.
Okay. But for example, the atmosphere is stratified, right? So and most of the wind turbine is above the surface layer, where the fluxes and then so on is assumed constant.
Yeah.
but then how you handle the certification of that atmosphere? Because there is you can say that, for example, above the surface layer is stable, but near the surface perhaps is unstable or neutral. How
Yeah.
you handle the certification of the atmosphere?
I'm not sure I can say that. I mean, two things. One, if you already know how the velocity profile would look like, you can
Yes.
put it in using with the body forces. That's one thing. So you can mimic any arbitrary velocity profile. And the other thing is that you need to do a kind of a precursor simulation with the low level jets. So you need to do a simulation with the Boussinesq equations, not just Navier-Stokes, but as a use where you have buoyancy terms in.
Yes.
Then you can do it. But I think that the low level jet is I don't think it's so complicated to provoke in your simulation.
Well.
I think the gravity waves are probably much more complicated to. But at least I don't do it myself, but I have colleagues. They are generating low level jets from the simulations by solving the Boussinesq equations. You know, where you also have an energy equation with buoyancy term.
And for example, okay, Alan, please go ahead.
Yes, but please, about another topic. My question is, how do you use aerodynamics to develop a control system for wind farms? And what are the strategies to couple these two different topics?
So if you want a strategy for a wind farm, it's I mean, we sometimes talk about wind turbines are greedy because they have a controller, and this control design such that it will optimum always the best it can. So therefore, the only way to really have a control of a full wind farm is that all the turbines they're communicating, and then you need a common subject, which is that they in total together should optimize the production. I don't think anybody has been capable of doing that in real life. We have a project on this Lillegrund wind farm. There has been some projects where they try to do that, but I don't think without any success yet. Then, of course, there has been a lot of different techniques for controlling individual wind turbines by using curtailment, as we say, so they produce less, having yaw regulation, where you avoid the wake from one wind turbine to the next. But in total, even though you can find, I think there has been a recent paper, I think it was a Chinese paper I saw a few days ago, where they, in some cases, could gain, say, 15% of additional performance by using yaw control. But if they translated that into a full year, then it was 0.3%. So that was only for one specific flow direction in one specific case. So therefore, you can do a lot of things, and it can seem very promising. But for a full year, it's typically not. So that's one thing to have in mind. So it's and what the developers and operators of wind farms say is that if you can assure, for example, 0.5%, if it's assure additional production, they would be interested. But if you come and say, I can give you 10%, and it's only for one wind direction, they are really not interested in that. So it is for an annual production. But an annual production, everything more than say 1.5% is of interest, because you could say from economic perspective, there's a lot of money still, because you have paid the turbines. So it's pure production, it's pure additional profit.
Okay, thank you.
Wow, nice. There is like a prototype in Delft which use like a pulse to try to dissipate more quickly the wake. It's economically viable the using this kind of pulse, because there is also a quite loads in the blades, right? Which try to pulse all the.
Yeah,
the
I
rotor
don't
of
know.
the wind.
Maybe that is for floating wind turbines, essentially. I'm not sure. I know they have a concept called the helix concept.
Yes. Yes.
Yeah, and it seems to work. But again, I'm a little bit skeptical for full production, but
Okay.
time will show if they can
Yes,
come up
yes,
with something.
Yes, yes.
Yeah.
Okay, nice. So sorry, I told you that I will take a little bit of time. I'm curious about the pairing of the helical vortex because I don't know if because I always think that one of the main reasons that the wake dissipates is because there is a first atmospheric turbulence that is transporting momentum into the wake.
Yeah.
And then you have the viscous and turbulent dissipation. So what do you think is a combination of all, or there is a or what do you think?
Yeah, I mean, even the model we made, I showed you this analytical model shows it quite well actually, because if you have a high turbulence intensity, say 10% or 15%,
Yes,
then
that's
this is really the dominant part. Then this induction is only a small part.
okay.
But they're both coexistent. Also, when
Okay.
we talk about meandering has been discussed a lot, and I have a very good colleague, Gunnar Larsen, who developed this dynamic wake meandering model that's used by industry today. And he never wanted to hear about that there are some self-induction. And of course there are, because you have von Karman vortex street, you have all these instabilities in the system. But he's right in the sense, if you're in the atmospheric boundary layer and the turbulence intensity is sufficiently high, this is the most dominant part.
Okay.
But on a cold winter day, for example, in northern of Europe,
Yes.
where there are very little, and offshore where very little turbulence, then the other thing can play a big role also.
Robert, the main of the weight is I don't know what is the effect of the surface roughness. I think sometimes I read about it, and there is if the wake goes too low to the surface, I don't know if it can happen the meandering of the wake.
Yeah, I mean the reason the meandering goes mainly parallel to the surface. If it was in free air, it was a spiral, but because of the surface, it will go back and forth, essentially in a horizontal plane, and that is due to the surface. But furthermore, also the surface has an impact also on the mixing. There was an article years back by Charles Menevaux, and I think it was maybe Johan Myers, or also Tony, I can't remember. But there they did a balance based on the large eddy simulation. They did a balance on the kinetic energy, where the different terms where turbulence produced and was transported and so on. And then they found out that there's a lot of in the mixing process, a lot of kinetic energy going between the two lines of turbines along the surface and up there. So you can find a very nice paper on that.
Okay. And finally, Professor, I don't want to your wife to get mad because of the dinner. There is a final questions, and what do you think about the deep learning model and CFD for wake modeling?
About the first, was it
the coupling of deep learning model, machine learning and so on.
Machine learning, yeah.
Yes, and CFD for wake modeling of wake forecast, for example, right? What do you think?
I try to say that if you do not have any equations, you don't know anything about your system, machine learning is nice. But if you know some physics, for example, Stokes equations or anything else, I would always prefer to do that. But one thing you can do is you can, in order not to do the same computation over and over again, you can do some computations, and then you can do reduced order modeling, for example, proper orthogonal decomposition or other things where you can kind of compress your data, and then you can use them in simpler models. But I would say that machine learning would probably be the last thing I would go to, because machine learning essentially is for systems where you don't know anything, but you need to find a pattern. You want to find a pattern in it.
Yes,
so I see it more like as a signal analysis or data analysis.
Okay, thank you very much, Professor. Yes, we need to finish also because it's you give us a lot of time. And okay, thank you very much for your excellent presentation. And I need to say that I admire your work and admire you, and you're my hero in academia. So thank you very much for accepting
Okay,
this.
thank you for the nice words.
Yes, and bueno, nos vemos para el próximo seminario. Estamos pendientes para el próximo. Será relacionado otra vez a CFD, pero ahora orientado a cuestiones de edificaciones. So, thank you very much, Professor. And
Okay, you're welcome.
And see
Have
you
a nice
soon.
day.
Bye.
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 Nice